Okay, good evening. This is Professor David J. De Los Reyes. Okay, it's September 10. The time is 9:16 p.m. Okay, my subject matter for this session will be alternating current machines, and we are now on lesson number 7. So for those of you who are following my channel on AC machines, this will now be lesson number 7. Okay, let's proceed. The subject matter for tonight will be AC machines, alternating current machines. This is lesson number 7. The title of the subject matter is Relations of Voltages and Currents at no load for a given transformer. So, considering for the meantime a transformer, we will be deriving the relations of the voltages and currents with the given condition, no load at the terminal, no load. That is just case number 1, because there will be other cases in which there will be load on the secondary. That's another thing. So for tonight, we will just concentrate on the voltage and current relations, okay? Considering for the meantime, there is no load on the secondary. The logic of the subject matter for tonight, like it is the same as on the so-called power generation. If on the generator side, you will be having 133,000 volts, and you will be delivering, this is storytelling guys, and you will be delivering this 133,000 volts 300 miles away, okay? What will be the receiving voltage, okay, if the wires that will be used will be a number 40 maybe. So it seems to bring out a certain voltage at the far end, 300 miles away, you will compensate for the voltage drops on the transmission line. You will compensate. You will add up a certain voltage on the generator side. So when it passes through the transmission line, okay, as it arrives at the course, what you call this distribution area, there will be enough voltage, okay, for the users to use, which is actually 120 volts. So how could you determine that if you deliver 133,000 volts at 300 miles away, will there be 120 volts maybe over there? Okay. For us to be sure that there is 120 volts, you will compensate for the transmission line losses. So also for transformer, okay, if the applied terminal voltage is actually, assuming it's 2400, okay, and there will be losses on the transformer, whether we like it or not, there will be losses on the transformer. This is the so-called, there are 2 losses in the transformer, the hysteresis. This is a little bit storytelling guys. We are not yet on the, what you call this equation side, and the eddy current loss. So, for transformers, the losses are actually termed to as hysteresis and eddy current. And if we try to read what is hysteresis and eddy current, hysteresis loss is caused by the magnetization and demagnetization of the core, meaning the lamination, as the current flows in the forward and reverse direction. We are mentioning alternating current here. So at one time the current will be in this direction, at other times the current will be in this direction. That's why it is so-called alternating current. It reverses direction for a 60 Hertz, okay? It will reverse direction 60 times per second, right? So the effect of that reversal of current 60 times per second, there is the so-called loss, and we term that loss as the so-called hysteresis loss. Okay? Okay, that's a storytelling, guys. The loss due to the reversal of the current 60 times per second is termed to as the so-called hysteresis loss. Okay? The other loss is eddy current. Oh, this is not eddy Ramos. Eddy current loss. occurs because of the relative motion between the conductor and magnetic field. It is due to the effect of the relative motion of the conductor and magnetic field. That is termed to as eddy current loss. These two losses are actually phenomena. We could not see this one, but according to our textbook, these are the definitions of hysteresis and eddy current loss. So it's up to us to imagine how come they came out, right? So the losses for a transformer, there are two. It will be the hysteresis loss. It is due to the current reversal for the primary windings. And the eddy current loss is due to the so-called relative motion between the conductors in magnetic field. Magnetic field meaning the flux or the magnetism. Because to produce a voltage, there should be a magnetism, right? Any conductor. The two requirements for us to generate voltage is that there should be a conductor and there should be flux or magnetism. And according to the study, the relative motion between the conductor and magnetic field is termed to as the eddy current loss. Okay, that's storytelling, guys. So if we go back now to the circuit diagram, this is we are given a single phase transformer, right? This is the applied voltage coming from the generator side, coming from the transmission line. This is R with the subscript P, small r with the subscript P, meaning primary internal resistance. Primary winding, the winding that is found on the primary side. Whether we like it or not, there should be an internal resistance because there is no such thing as a perfect conductor, right? There should be a small resistance, very small, maybe 3 ohms, 4 ohms, okay? What's the next one? Capital letter X with the subscript P, meaning inductive reactance. Why there is an XP here? For a coil, whether we like it or not, there should be a reactance. That's one of the characteristics of a coil, okay? Internal resistance and reactance, we could not avoid those ones. So in the computation of voltages, we must have to, what we call this, consider these two values here. Because there is an effect, right? That's why there is this so-called voltage drop due to these two here. Okay? What's next? The current coming in on the primary, no load on the secondary, is termed to as capital letter I with the subscript NL, meaning no load current. Okay? This will be the current that will enter the transformer, okay, when there's no load on the secondary. So assuming you plug in your transformer and you don't put any load, okay, whether we like it or not, that transformer will get heated, right? Why it warms up? Due to the so-called losses, okay? Even though there is no load on the secondary, the transformer will get warmer, right? So if you forgot to remove your transformer for 1 year, it might explode, right? Why it explodes? It is because with the so-called hysteresis and eddy current loss, okay? There will be a current that is the effect of the relative motion of the conductor and magnetism, even though there is no load, right? And the hysteresis loss is actually the current of the secondary keeps coming in and out, even though there is no load on the secondary, whether we like it or not, because it's plugged in, right? There is an applied voltage here. There is no load, but there should be current going in, very small current. It seems like just like in the so-called microprocessor, okay? If you are not using your microprocessor, that microprocessor is actually consuming current. Okay, it's consuming current because without that 5 volts DC for a microprocessor, it will not work. As soon as you push the pause button, it will not work if there is no 5 volts over there. So a microprocessor should always be plugged in before you push that pause button. What's next? The induced voltage on the primary winding is designated as capital letter A with the subscript T. And the total number of turns on the primary will be capital letter N with the subscript P. For the secondary side, it's the same. Instead of RB, it will be RS. Because there is a winding also on the secondary, right? So there is also a reactance effect of the winding on the secondary. It should be designated by excess. Okay. There should also be an induced voltage on the secondary, and there should also be a total number of turns on the secondary. The voltage at the terminals over here, okay, no load for the meantime, we call it BS. This BS here is actually the one we are getting from the California Edison. It's 120 volts, right? So meaning to say, if the transformer got no load, there is a standby voltage at the terminals of 120 volts. There is no load. So as soon as you plug in your load on the secondary, there will be a secondary current. But for the meantime, we are only discussing, okay, that the secondary side got no load. Okay, we will be deriving the relations of the voltages in current when there is no load on the secondary. What's the importance of this? The importance of this is that to determine the so-called value of the no-load current. I, capital letter I with the subscript in L, meaning no-load current. We are interested in this one. Why we are interested? Because if we try to design our transformers, it's a must that we should know the value of the no-load current. Because the no-load, by knowing the no-load current, we can determine the product of I times J, and this IC is actually the so-called voltage drop. Voltage drop, right? Because voltage drops in the so-called power generation or voltage generation is very important. If you don't compensate for the voltage drop, okay, there will be a problem on the output voltage of the secondary. If you do not compensate, because if you do not compensate, maybe the efficiency of California Edison might not be high, because if you try to plug in your maybe your motor over here, it will not turn the correct RPM because the voltage coming out is very low, right? So for us to maintain the correct rotation of a motor that is plugged in on the secondary, it's a must that we should compensate for the voltage drop. So this is actually used in the sole design of transformers. Okay, let's proceed. I place it here. Capital letter I with the subscript and L, meaning no-load current, equal to capital letter I with the subscript HE plus J, capital letter I with the subscript EX, meaning the hysteresis current plus J, the exciting current, is actually the no-load current. And this IHE is actually the current due to the hysteresis loss. And this exciting current, where's exciting current? Oh, I don't have any discussion on exciting current. Oh, exciting current. The current that is in phase with the neutral flux. Okay, let's try to, what you call this, analyze this given equation by using a vector diagram. It is like this. This should be the y-axis, or the vertical line. This is the horizontal line. And for the study of alternating current machines, the direction of the flux, if we try to bring out the vector diagram, it should go up. This is the mutual flux. It's go up. So it seems it's on the y-axis. And according to our annotation, the exciting current is in phase. No, is it in phase? Or the hysteresis? The hysteresis is actually in phase. Oh, the hysteresis. The hysteresis is actually in phase with the mutual flux. Okay? The exciting current due to hysteresis, yan. That is I with the subscript HE. According to this annotation, the exciting current, which is due to the hysteresis, and it is designated as capital letter I with the subscript HE, is in phase with the mutual flux. So if we try to bring out the vector diagram, if this is the mutual flux, this is the hysteresis law, the current due to the so-called hysteresis laws, that is capital letter I with the subscript HE. Okay? And the exciting current, it goes to the left. It is this. So the vectorial sum of IHE plus I exciting, it has actually just this equation here. The vector sum, it should be I with the subscript and L. The vectorial sum of this side here plus this is actually this triangle here. Right? And in phase with this, this is the no load current. Right? And in parallel with this is actually the product of, in parallel, this side here. It's the product of the no load current times R sub P. They are what? They are in the same direction. This one here are these ones here are parallel, right? This is the no load current. This is the product of no load current and R sub P. It is the voltage drop due to the effect of the resistance on the coil. This side here. And perpendicular with it is the product of no load current times X of P. Perpendicular. So this is a right triangle. Right? So the vectorial sum of, this is EP, originally, this is EP. EP, the induced voltage. This is EP. Okay, this is the product of I no load times RP. And this is the product of I no load times 6V. Am I still on camera? Okay. So the vectorial sum of EP plus the product of IN RP and the product of IN times 6V is actually BP. You got it? What's the significance of this vector diagram? If we try to visualize the vector diagram, it means that this figure here is just this equation here, this one. Meaning, the applied primary voltage is equal to the induced voltage plus the impedance drop due to the so-called RP and XP. Okay? So, which is bigger here? Is it BP or EP? It's BP. BP is bigger. It is like this. If this is 200, 405 volts, 2405 volts, okay, to obtain a voltage of 2400 on the primary, okay, meaning to say there is an impedance drop here of 5 volts. It is something like that, right? A 2405 minus 5, assuming for the meantime they are all real, what comes out on the primary, on the induced voltage on the primary is 2400. That's the one I am saying that you will compensate for the impedance drop. Because as they passes to the RP and XP, there will be an impedance drop whether we like it or not. The voltage that will come out here will be lesser. Right? Because if you then compensate for your BEP here, if this is only 2400, right? And there is a drop of 5 volts here, what will come out here will be less than 5 volts, 2395, right? It is not exact to be 2400. So for this to be 2400, okay, you will compensate for that voltage here by adding something over here. So on the so-called generator side, okay, because generators are also designed. You will design how much will be the RPM, how big might be the generator. So actually, you will be knowing what will be the output voltage of the generator before they are fed to the transmission line. Okay? So the logic is the same as here. The applied voltage on the primary should be greater. Okay? As it passes through RP and XP, it will be lessened. So actually, BP is bigger than EP. It is this equation here. So the current and voltage relation for a transformer at no load is the current relation will be this. The no load current will be the current due to hysteresis loss and the current due to the so-called exciting loss. Okay? And for voltage, the applied terminal voltage Vp should be equal to Ep, the induced voltage, plus the impedance drop, in which the vector quantity of R sub P plus Jx sub P is termed to as the primary winding impedance. Okay, that's it, guys. That is how we arrive at a certain voltage on the other side. Okay, and to compensate for the losses, we must have to include the effect of the resistance and inductance loss plus the so-called in the current computation, there is the effect of the hysteresis and the other losses, right? That is the eddy current and the hysteresis. So, when we are talking losses over here, okay, initially we talk to the losses as on the current portion. Then as soon as we compute for the current portion, okay, we will bring that current to the computation of the voltage. So it means we actually use these values here. Okay? Okay, that's it, guys. How we produce a voltage at the other side or on the induced voltage. We must have to compensate for the losses due to the hysteresis and eddy current and due to the effect of the resistance and reactance of the transformer. Okay, good evening from Los Angeles. This is Professor David J. de los Reyes. Our topic was the voltage and current relations for a transformer if there is no load on the secondary. Okay, good evening from Los Angeles.